Hey everybody, Dr. Segrin. I am recording this one from home, so pardon any dog noises you hear, which might include Loki's heavy breathing right now. Loki, can you please leave me alone? So I'll be a little bit distracted here, but it's okay. I'll make it through this. And today we're going to be talking about global warming and climate change. And that's what we will be talking about for the next several lectures. I really can't stress to you the importance of this issue, but I'm going to try in this lecture today. You cannot be panting over my whole lecture. Why are you breathing so loud? What do you want? You want to just say hi to everybody? Okay, yes, we all see you're a lovely dog. So far in class, we've talked about a few environmental issues. We've brought up the issue of dead zones, how human waste and fertilizer runoff and animal waste running off into rivers and lakes and finally into the ocean creates this explosion of algae and ultimately a dead zone where not much survives other than algae. That's obviously a pretty big issue in the world. There's some other issues like other types of water pollution. We've talked about oil spills before, and an issue that we haven't covered yet is plastic pollution in the ocean. Plastics take forever to break down naturally, so when people litter them around the world, typically they wash down rivers and into the ocean, and so we have massive amounts of plastic in the ocean that's just kind of sitting there, and it's going to sit there for hundreds of years. That's a huge issue. We've talked a little bit about air pollution, how certain kinds of activities, burning of fossil fuels, creates massive amounts of air pollution and can cause asthma, emphysema, different issues for people around the world, and as well as acid rain, which can damage ecosystems. Again, another really big issue around the world. We've even talked some about resource depletion, how humans almost entirely depend, our entire economy basically depends on non-renewable resources that we are running out of. All of those things are horrible that are happening in the world, but I could conceive of a way to make those better. And in fact, there have been instances in time where people have taken action to clean up rivers and oceans and the air quality. Global warming, this topic that we're about to begin discussing, I think if you take all of those combined that I just mentioned, and probably multiply it by many times over, that is the kind of magnitude of environmental destruction that we're talking about with global warming. So I'm kind of left with this massive issue that's super complex. It's like, how do we possibly begin this topic? And I've decided to start today with our first of many lectures on the topic of global warming and climate change. I'll explain the difference between the two momentarily, but we're going to start with perspectives in paleoclimatology. It'll kind of make sense why we're starting here, because it will definitely convey the magnitude of the situation to anybody who's watching. And paleoclimatology is basically the study of ancient Earth climate. And studying the ancient climate of Earth can give us a lot of insight into where we are currently heading. So let's get right into it. So if we're talking about ancient climates, we probably should start with what is a climate. What does that word mean? Generally speaking, climate can be summarized as the average temperature, rainfall, and wind of a region. So pretty much the weather, but over a long period of time. So when we talk about, hey, how's the weather outside? Generally, you're talking about the temperature outside. Is it raining? And how windy is it? Those would be the main factors that people want to know in their day-to-day lives. And so when we talk about average trends in these, so for example, we can talk about the average summer weather of Houston, that's where I live, or the average amount of rainfall we would typically get in the summer, or the average amount of windiness for our region. That would be the climate of Houston. And you can compare, say, I don't know, the climate of Houston, so talking about average temperature, rainfall, and wind, compared to, I don't know, the climate of Alaska. And we would see, okay, the climate of Houston is considerably warmer. We get more rainfall, and I'm not entirely sure, probably less wind than a typical climate in Alaska. So that's how we use the word climate. It also includes the average extremes you would expect. So for every place in the world, yes, you have a kind of typical average climate, but then also within that, you do get extreme years, or maybe even extreme decades of weather, where you might have a drought every once in a while, or a big flood every once in a while. Those are all also part of climate. Something that's interesting about these is that all of those processes, when it comes to temperature, obviously that's driven by heat, so how much heat is in the area. But rainfall is driven by evaporation, so that's a heat-driven process as well. And wind, the reason the wind is blowing ever is also a heat-driven process. Parts of the world heat up, parts of the world cool down, and wind blows based off of that principle. So when we talk about the word climate change, which is the subject of this series of lectures, climate change would represent when there's some shift in either the average or in even the extremes that you see for a region. If you're seeing a change in temperature, a change in rainfall over many, many years, that would be evidence of climate change. So for example, in my city, Houston, if we look at the summer temperatures, June, July, August, those really hot months for us, I think September as well, we see that the temperatures are rising over time. So if we look back at the last 50 years of temperature data, for summer months, for the maximum temperature, back in 1970, typical temperature maximum was around 90 degrees, whereas today it's more like 93 plus degrees during those summer months. So that would be an increase overall in the average temperature, and so that would be climate change. And also within the last 5 years here in Houston, we had Hurricane Harvey, which represented a flood that was the biggest flood in the history of Houston, and actually the biggest rainfall event caused by a hurricane, I believe, in U.S. history. So that was an extreme event that happened, and that could also be a sign of climate change. What we are seeing is around the entire Earth, if we look at the average temperature everywhere, everywhere in the world, every country, every ocean, everywhere on the Earth, we can see that the overall temperature of Earth is actually rising. That is global warming. So global warming and climate change are kind of the same thing, but not quite. Global warming just refers to the idea that, yes, the average temperature on Earth is increasing if you look everywhere at the same time. Climate change is the more nuanced. Okay, yes, the average temperature on Earth is increasing over time everywhere. Some places faster, some places slower, and that is bringing all kinds of different changes to things like rainfall, wind patterns, temperature patterns, etc. So climate change is kind of like the more nuanced and bigger picture of global warming. And I want to kind of get into that a little bit more here by describing to you Earth's kind of normal climate system as it is today. And the first thing to understand about Earth's climate system is that it is all heat driven, and heat is a chaotic thing. By its nature, actually, the definition of heat is just chaotic motion of particles at the tiniest level. So if you could somehow look at atoms and molecules around you, in the air, in the water, even in solids, what you would see is that they all have a motion to them. And if you increase the amount of heat, the motion that they have increases as well. But this motion is purely chaotic. You can begin to see that here in this top right picture. This is what we call turbulence of a fluid. So anytime you have motion in a fluid, you pretty much get turbulence. And turbulence you can kind of just see as this kind of random chaotic swirling of this fluid. But what you kind of notice is that it kind of gets smaller and smaller and smaller as it kind of forms these little eddies and stuff. And as it gets smaller and smaller and smaller, that chaos never really goes away. It just gets smaller and smaller and smaller. And we can't see it really at the tiniest of tiny levels with even powerful microscopes, but it's still there. And that chaotic swirl is basically what heat is at the tiniest level. It just so happens that at really, really large scales, when you have heat that's added to Earth, say, we get kind of this massively chaotic swirl action as well over the largest scale. So this is the tip of Spain here, and these are ocean currents within the Mediterranean Ocean, and you can see all this chaotic swirling action. And that all of that motion is caused by heat as well. And when you look at the actual atmosphere, this is a diagram of some of the motion in the upper atmosphere, I believe. You can see these kind of random swirling wind currents, the exact same thing. This is basically the wind blowing. And all of this kind of chaotic motion is actually driven by something called convection. And I showed you convection earlier this year, but maybe we should revisit that little recording. So yeah, what you can see there is that if you put a hot fluid next to a cold fluid, there's a tendency for the hot fluid to go on top and the cold fluid to push down to the bottom. And that same tendency is basically what's happening to air and water currents around the world every single day. When we're talking about the overall temperature on Earth increasing, which means that the overall amount of heat on Earth is increasing, we can see that that's going to manifest itself in potentially altering a whole lot of things. If all of the motion of the ocean and the air is dictated by heat, swirling around with these chaotic currents, if we're adding more and more heat to the system, we can see that that's probably going to change a lot of things. And the story gets a little bit more complex if we're talking about Earth's overall climate system and this sort of system of moving heat. Basically, when we analyze this motion of air and water, we can draw out some pretty broad patterns. So as the sun shines on the Earth, there's actually more sunlight, if we want to call it solar density or radiation density. Basically, the sunlight is more focused on the equator compared to the poles. And this can kind of be explained like if we imagine, so here's the Earth, and here's the equator, and here's the North and South Pole. You can imagine your person on the Earth here, you're going to be standing this way. And the sun is kind of shining directly through the atmosphere right down on top of you, pretty much constantly all year. There is an axis, a tilt of the Earth that changes with the seasons, but for the most part, if you're this guy at the equator, the sun is going to be directly overhead most of the year. Whereas if you're at the North Pole, you can see that the sun is, the angle at which it's approaching the atmosphere is actually kind of more slanted. What that means is that there is a lower density of sunlight hitting the pole up here. In other words, the same amount of sunlight is actually spread over a larger area of the pole. Another way to think about that is when the sun is directly overhead, shining right down on you, that's kind of really, really hot, and you can really feel that heat and intense. When the sun's on the horizon and the sun's rays are kind of approaching at an angle, that is the sunlight is really not that intense, and that's sort of what the North Pole is experiencing year round, is that sunrise sunlight that's approaching at an angle, and so it's really just not very intense. So ultimately, what this pattern means is that over time, the equator gets pretty hot, and the poles are going to be cooler. If you've ever wondered why the equator was so warm, the poles are so cool, that's it. However, when you put hot and cold next to each other, we know from our little experiment that the hot will kind of move in one direction, the cold will kind of sink in the bottom and move the other direction, and there's going to be a circulation of convection that transfers heat from the equator to the poles. And then on top of that, so that's the general pattern here is going to be heat is going to move up to the poles, and down here where the cold water is, it's going to generally sink down to the bottom and then move back in the other direction along the bottom. So we could expect some kind of pattern like that emerging from this principle. But something that kind of throws a big wrench in it is something called the Coriolis Effect, and also the location of continents. So this is our heat distribution of Earth. You can kind of tell where it's basically red is where you get the most solar intensity and the most amount of heat that's absorbed. And where it's blue, you get the least amount of solar intensity and the least amount of heat absorbed. And again, we're going to expect some kind of shift of this heat. This big pocket of heat is going to tend to move this way on the surface, and there's probably going to be some counter current of cold water moving down below it, just like we would see in a lab experiment. What the Coriolis effect does is basically cause things to spin on Earth. And the Coriolis effect is one of those things that once you get it, it makes sense, but it's kind of a hard principle to get. It all has to do with how the Earth is spinning. That's what creates day and night. But if you imagine somebody here on the equator compared to somebody up here on the, near the North Pole, what we see is that each of them is spinning, right? On the Earth, let's say the Earth is spinning this way. And each of them is spinning and doing one rotation each day. But what we notice is that the distance that the guy at the equator is going is really, really big. And the distance that this guy up near the pole is covering is pretty small. So this is a large distance at the equator and a small distance here at the pole. And what it actually means is that, again, so I think the distance at the equator, say, would be like 25,000 miles. I think that's roughly what it is. Pretty far distance, and he's spinning that each day, right? So he's going 25,000 miles each day. The guy up here at the pole, maybe he's only going half that each day. And so what it means is that the person at the equator is actually moving really fast, and the person up here towards the pole is actually moving relatively slow. So what you can kind of imagine to understand this principle is that imagine that person at the equator has a really amazing football arm, and he's going to try to throw a football several thousand miles up to the guy up here at the pole. When he releases a football, there's our football, amazing football. So he's throwing this football up, and the football is moving really, really fast this way when he releases it, because it's also spinning with the equator, so it's got that motion kind of built into it. As it's moving further and further north, in this case, everything around it is moving slower than it. When we're talking, it's moving this direction, right? Everything around it is moving slower than it. So what it looks like is basically it begins to curve, because it is moving faster in this direction than everything that it's encountering. And the further north it moves, the faster it's moving compared to everything around it. And so it gives this kind of illusion of a curvature, because it has this kind of angled velocity going on. So that faster motion is actually at the equator is what's producing this Coriolis effect. And what it does is basically it curves anything that's moving from the equator to the North Pole is going to curve and tend to spin clockwise, and everything that's moving from the equator down to the South Pole is going to tend to spin counterclockwise in the opposite direction. And it's this insane effect that we see. And actually, all of these little spinnings that you see here pretty much are the Coriolis effect. And it's not always perfectly counterclockwise, but the majority of them are counterclockwise. Sometimes there has to be a counterbalance. So that is something that happens. And ultimately, this creates a picture of Earth's heat circulation in the ocean as well as in the air. So convection works for any kind of fluid. So as you heat up this area near the equator, the tendency is the hot air is going to rise and push upward, and then cold air is going to return back down to the south. And that's the overall trend that you get. But you also get these crazy spinning effects of these big air motions as they're trying to get heat from the equator to the poles. And so you actually get this insanely chaotic, crazy picture going on of what's actually happening on the Earth. It's all driven by heat, with some minor effects of where continents are, where mountains are, as well as this Coriolis effect. And a similar pattern can be seen in the ocean. You have a bunch of heat here. Generally speaking, that's going to push up to the poles, and then cold water is going to come back down on the bottom. That cold water's got to rise somewhere, and this massive conveyor belt in the ocean begins to form, but then you also get all these rotational fields going on due to the Coriolis effect. And then, of course, you have continents in the way, so the water is blocked in some areas. And so what emerges is basically this unbelievably complex system of air and ocean currents that are actually taking place on Earth. An enormous question that scientists kind of have to tackle is, as the Earth overall seems to be getting hotter and hotter, the overall average amount of heat begins getting hotter and hotter and hotter. How is that going to affect this distribution of all of this air and water that is kind of naturally all being driven by heat? As we add more and more heat to this system, what's going to happen? I think logic would dictate that it would potentially begin moving faster, which it does in certain areas, but there's some counterbalances that could make it move slower in certain other areas because cold water needs to sink. And if you keep heating it up, it can't sink properly. And so all this is to say that we are, when we're talking about global warming and the issue of global warming, the complexity of what it actually means for our climate system, we can't really begin to understand it. To kind of help you understand this complexity, okay, Earth is getting warmer as on an average, but what we're actually seeing is that certain regions of the Earth are actually heating up much, 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 much faster than others, and certain other regions are actually getting cooler. And so why is this happening? It all has to do with exactly how, as we add more heat to this climate system, how is it being distributed around the world by the wind and the ocean currents. And then some places you can actually see are getting cooler. For example, this big pocket here. That's odd. So this must have something to do with wind and ocean currents? Yeah, sort of. There's a whole bunch of ice right here. And as this ice is heating up more and more, it's melting like crazy, and all this cold runoff is basically being dumped right here into the North Atlantic. At the same time, you have warm water wanting to push up into here, and colder water is going to need to sink down and come back down here. And what you begin to see is that this crazy exchange of heat moving around the world is having all kinds of insane effects, potentially in completely other sides of the world, because the entire climate system is interconnected by these ocean currents and these wind currents. Hopefully you've grasped that this is going to be a super complex issue. We're going to do probably an entire lecture on what exactly is happening with this ocean current and the importance of that coming up. But you can see part of the reason why we've kind of shifted away from using just the simple term global warming is because climate change is basically how global warming is actually going to impact the various regions of the Earth. How are the climates of all these different regions going to be impacted, and how is the heat that's moving around the Earth going to impact those climates? That is the more nuanced view of climate change, and hopefully now you begin to understand that. Okay, so we've been talking all about global warming, and we're saying that the Earth overall is getting hotter. Earth has an unbelievably complicated climate system that depends on the circulation of heat, both in air and in the oceans. And we know it's getting hotter, but that's causing different effects in different regions of the world, different effects due to how the ocean currents are moving and the air currents are moving. But why is this happening? That is the next question I want to explore. And I want to talk some about paleoclimate data to help explain that. So is this a natural process or is this man-made? So we'll come back to this question after I get done describing some of Earth's climate history. To start out talking about Earth's climate history, let's just kind of begin talking about this subject of paleoclimatology, the study of Earth's past climate. So basically our central question of paleoclimatology is basically, has Earth's climate always been how it is today? And the way we study the ancient history of Earth, again, scientists don't have time machines, so everything that scientists study, they have to be able to find on present day Earth and try to get a glimpse into the past. And the way we do that is by studying what we call proxies, or which are basically ways to approximate the Earth's climate in the past. One pretty simple climate proxy that I think most people understand is the idea of tree rings. So when you cut down a tree, you will notice that it has these different rings to it. And we see that in wood and stuff too. But what these tree rings actually represent is a year's worth of growth. During the springtime, conditions are good for growth. You have lots of moisture typically, and also a good amount of sunlight. And so what we see is that trees tend to grow a lot during the spring. And as they grow a lot, you kind of see this big ring form, because as the tree is growing bigger and bigger and bigger, it's growing out and out and out and out and out. But during the summer, as things get hotter and drier, typically that growth kind of stalls and you get a little bit of growth still, but it's kind of marked by this darker line. Because again, the conditions are a little bit drier, it doesn't grow quite as well. It grows a bit, and then during the fall and winter, most trees don't grow much at all. So these dark lines are basically indicative of the end of the growing season, which mainly happens in the spring. And then next year comes around, and in the springtime again, the tree starts growing more, and then we get another band. What we can tell is that sometimes these lines are really, really fat, and that represents a good year, so where there was lots of water. And then every once in a while, these lines get super, super thin, and that would represent a drought, where the tree couldn't really even grow much during the spring because of that drought. So we can analyze these tree rings and actually go back and count the years and count the little lines and say, oh, okay, 15 years ago, we had a drought. And some trees are hundreds of years old, and so we can count back hundreds of years and say, oh, there was a drought this year. So it's a way to basically study the climate of a place potentially hundreds of years ago, just by looking at tree rings. And we also have very sophisticated techniques to do something similar, but looking back thousands, tens of thousands, hundreds of thousands, even millions of years back into the Earth's past to study the climate. And these techniques all involve oceanic sediments and ice cores. So similar to tree rings, which kind of form a layer each year, there are parts of the ocean and parts of glaciers in places like Antarctica that basically each year a new layer of snow or a new layer of sediment at the bottom of the ocean is kind of laid down, and year after year after year, more and more and more snow and sediment is basically laid down in a stack. And so what you get is, you can kind of see it here. This is a ice sample here in Antarctica, but what you can see is all these layers packing in. And each of these layers would be each year during the winter, presumably a bit of snowfalls. Parts of Antarctica never get above freezing, so the snow never melts. And so year after year, we just get new layers. And these layers actually go down several miles in some parts of Antarctica. And what scientists can do is go drill into those and extract what's called an ice core. That's this thing over here. And they can begin analyzing the chemistry in those layers. The sediments and kind of layers of snow basically can tell scientists and give them some approximations of what Earth's climate was like for different years in the past. And because some of these layers are miles and miles deep, we can go back potentially hundreds of thousands or even millions of years back in time. And we basically have a nice little snow sample from 1 million years ago. Pretty cool. All right, so I do want to touch on, I don't want to just say magically the scientists figure out the chemistry and of these snow and they can tell what the temperature on Earth is. I do want to go a little bit into the science of that. However, the science of this involves something called isotope fractionation. And so it's a little bit complex. So I'm going to try to give you kind of the simple and easy way to understand it. So let's take a look at a diagram and do our best to understand isotope fractionation. Probably should start with what an isotope is. All right, so isotope fractionation and a little bit about Earth's climate history and what information we can get from these ice cores. So an isotope, we have already had a bit of a chemistry refresher in our environmental science course already, but as a refresher of what an isotope is, we know there are different elements of things on Earth like carbon, oxygen, hydrogen, okay? And what makes an element is the number of protons. And that is a big focus when you take chemistry, is all the different protons and elements and stuff. What sometimes isn't paid attention to as much is neutrons. Neutrons, when you add more and more neutrons to an atom, it doesn't change the element. It doesn't change very much of anything about the atom in terms of how it behaves, with the exception that as you add more neutrons, the atom gets heavier, which means that it's kind of bogged down. So an isotope is basically when you have two of the same element that have different numbers of neutrons and different masses. So an example of that is oxygen. We say there's oxygen 16 and oxygen 18. And the only difference here is that oxygen 18 has 2 more neutrons to it, so it's heavy. So normal ocean water, and then this oxygen 16 by contrast is a lighter isotope. So both of them are naturally occurring in the ocean. They're both harmless, so if you go drink water, you're drinking lighter and heavier oxygen in that water for your H2O. You're made of a mixture of these isotopes. The ocean is made of a mixture of the isotopes. They behave pretty much the exact same, with the exception of because the oxygen 18 is heavier, a process like evaporation, where the particles of water are heating up and need to escape liquid form as a gas, what tends to happen is that when you have a process like evaporation, the light isotopes, oxygen 16, are generally going to be the ones that evaporate, and the heavy isotopes are typically going to be left behind. So scientists have kind of figured out that what they see is that when they analyze sediments in the ocean or sediments that are in ice on land, they see different patterns of these isotopes emerging. So they see periods of time where there are more heavy isotopes in the water, and they see periods of time where there are more light isotopes on land. And they were kind of asking the question of, why are we seeing that? So in other words, as they studied these different layers, they see a pattern where they see more light, more heavy, more light, more heavy, more light, etc., etc. Scientists were looking at these different bands, and they had a suspicion of what maybe they could mean based off of what was already pretty commonly accepted, that at some point in Earth's history there had been an ice age. scientists for a while, even back in the 17 and 1800s, had suspected that Earth used to be a lot colder than it is now. The reason for that is there's lots and lots of evidence of glaciers all over the place in the northern hemisphere. For example, you get these valleys. They're called U-shaped valleys, and typically when you have a like a river or something flowing through a valley like this, you would kind of have like a canyon in the middle, but this U-shaped valley is typically made when you have ice that's stuck in it and that is slowly sliding downhill as it's melting. So as you have, which is a glacier. And they saw that some of these, there are still active glaciers in mountains and they see these forming, but they would find these sorts of U-shaped valleys in areas that don't currently have glaciers. Something else scientists find are these boulders that are just kind of dropped in the middle of nowhere, sometimes next to these U-shaped valleys. And they're like, how could these boulders have gotten here? There's no rocks like them in the area. There could not have been blown there. I mean, it would take unbelievable, like the strongest tornado ever to lift one of these things. It probably couldn't have been washed there. I mean, it would take like the biggest, fastest moving river ever couldn't move one of these. So like, how in the heck could these boulders have gotten here in the middle of nowhere? And the idea is sometimes when you have these glaciers sliding down these hills, they pick up all kinds of boulders and debris, and then when they melt, they kind of drop them back on behind. They're called glacial boulders. You would see these scrapes on certain parts of the rock, which are typically made by ice freezing in them. You also have glacial deposits, which are kind of like, not quite boulders, but big pebbles and stuff that you see big layers of them. And, you know, there's no evidence of a river or wind being able to carry them. And so the assumption is ice. And you see these evidence of this all over the world. So scientists, when they're looking around, they see it all over the northern hemisphere, all across this area, even down into like the northern United States and all across Europe. You see this. And so the assumption is, well, at some point in Earth's history, there must have been a whole bunch of ice. And so the knowledge of, okay, there was a previous ice age was pretty widely accepted. And then scientists were looking at these patterns of light and heavy isotopes, and they kind of put it together that these patterns of isotopes were actually being caused by cycles of ice ages happening. And basically what's happening is that vast majority of water on planet Earth is in oceans. And pretty much the only other significant deposit of water on Earth are glaciers. And when you see a band of sediment in the ocean that has many, many heavy isotopes, the assumption is that all the lighter isotopes must have evaporated, fallen as snow, and then made some massive glacier somewhere. And then in that ice sample, you would see lighter isotopes. And so basically scientists analyzed these bands of light and heavy, and the pattern that emerged looked like this. And so this might be something you didn't know, but actually when we're looking at these isotope ratios, I think this is probably an ocean sediment core based on how far back it goes. So we could say this is the heavy isotopes. And so when we see more heavy isotopes being left in the ocean, we can assume that all the light isotopes are in ice on the land, and so this would correspond to an ice age. When you see not very many heavy isotopes in the ocean, so more lighter isotopes in the ocean, that means that all the ice is melted and all those light isotopes have returned to the ocean, and so those would be a warming period. And what you see is that it basically goes back and forth. Ice age, warmer period. A little mini ice age, warmer period. Ice age, warmer period. Ice age, warmer period, etc., etc. This was a pretty big realization for scientists, that basically Earth's climate has changed a lot over the last million years, and that climate change is actually a natural part of Earth. I'll keep watching because we'll talk about what's happening currently and put it in some context to this. But the other realization is that ice ages, as scientists were studying all these phenomena they're seeing, I think the general assumption is that there was probably one ice age at some point in Earth's past. And what we realize is that no, there were actually multiple ice ages, and that actually they kind of follow a pretty distinct pattern. That basically you would see one ice age every 100,000 years or so. And the last ice age that happened was about 20,000 years, which is when Eastern Asians crossed over into North America, but I digress. Most of modern human history, basically written human history, has all actually been in a warm period of time, basically the last 10,000 years or so. So the picture that's kind of emerging here is that not only is Earth's current climate system really, really complex, but Earth also, when you stretch back and look way, way far back in time, we can see that there is amazing complexity in terms of what's been happening to the overall climate of the entire Earth in terms of various heating and cooling cycles. And just for some perspective of this last ice age, this is the estimated amount of ice that would have been all covering various cities in North America. And so the city of Chicago would have been buried in 900 meters of ice during the last ice age, which that's like half a mile of ice on top of Chicago. So yeah, this ice age was no joke. I mean, talking about a completely different world than what we are currently living in. All right, so here's where it gets a little bit even more interesting. So when we look at the isotope data that's showing these ice ages, where you get to, warmer periods and then a colder period and then a warmer period, what scientists noticed was that each warm period, and again, this is in the ice core samples, within the ice core, if you didn't know, all ice has tiny little air bubbles in it, and scientists were able to analyze those air bubbles, and those air bubbles are basically trapped air from Earth's past. So as scientists are looking at samples of this ice that's been buried for millions of years, thousands of years, hundreds of thousands of years, not only do they have a water sample from the snow that was falling at the time, but they also have an air sample of the atmosphere at the time that's trapped in that ice. So when they analyze the air sample, they can figure out how much carbon dioxide is in it. We'll talk about carbon dioxide in a second, but what they notice is that when carbon dioxide is really, really high, it tends to correspond to a warmer period. And when carbon dioxide is really low, it tends to correspond to a colder period of time. So here's years ago, see these ups and downs of the temperature, where the cold would be the ice age and the warm would be the, what we're living in right now. And you can kind of see that these patterns almost perfectly mimic each other. So it seems like carbon dioxide is a pretty important part of what's happening to the temperature on Earth, and that's not too surprising. We know we've talked about so far in this class, something called the greenhouse effect and greenhouse gases. So gases such as carbon dioxide, CO2, or methane, which is CH4, trap heat from the sun. So greenhouse gas is a gas that traps heat from the sun. And this is kind of how we can visualize this. And this is actually what our next virtual lab experiment is going to be about, if I can get it all filmed. We have sunlight hitting Earth. Naturally, some sunlight will be reflected back out. And also, there would be some infrared radiation escaping Earth back out. What a greenhouse gas does is basically traps this infrared radiation, this heat radiation from escaping Earth, and that makes Earth hotter. So it's not too surprising that as we see more carbon dioxide in the atmosphere, that we would expect Earth to be hotter. And when we see less carbon dioxide, we would expect less heat to be trapped in the atmosphere, and Earth would get colder, like an ice age. There is one last key to kind of understanding these ice age cycles, and that is how regular they are. When you look at it, about every 100,000 years, we get a warm period, and about every 100,000 years, we get a colder period. And it's a pretty regular pattern, especially in the last 400,000 years. And then in the previous 400,000 years, it's not quite as clear. So why is the carbon dioxide, if it's caused by carbon dioxide, why is the carbon dioxide going up and down over time? What process could drive that? That is a very complex question, and we'll get back to it in a second, but we actually believe this ice age cycle is partially driven by greenhouse gases, but partially driven by something called the Milankovitch cycles. The Milankovitch cycles are basically, you know, I think a lot of people forget that we are on a planet that is orbiting the sun, and this whole solar system formed out of a giant mass of a supernova. And so it's a bit chaotic. And a scientist named Milankovitch, I believe he was Serbian, noticed that as Earth was going around the sun year after year after year, that the positioning of certain stars and stuff was actually changing. You know, the angle that you could see them in the sky was very, very slowly changing. And he put it together that there's actually three kind of weird things going on with Earth. Earth's tilt actually changes over time. So sometimes the Earth is more tilted and sometimes the Earth is less tilted. That tilt is related to seasons. So when the Earth is more tilted, you get more extreme seasons, for example. With more tilt, you get more extreme seasons because the tilt is more severe. When it's the wintertime, you're tilted further away, and when it's the summertime, you're tilted even closer, and so you get more extreme seasons, hotter summers, colder winters, when you have more of a tilt. The tilt itself kind of wobbles, and that affects what parts of the continents are getting the most sunlight and whatnot, and then also the Earth's orbit itself kind of stretches out over time. And the big takeaway is that when people began analyzing the ice cores and Milankovitch cycles, they kind of noticed that they sort of lined up. When you had a more stretched out orbit of the Earth, that typically lined up with warmer periods. So this would represent, this hump here is how stretched out it is. So when you see the top of the hump here, you see that typically that's always a warmer period, top of a hump, warmer period, top hump, warmer, top hump, warmer. And you can see different, basically all of these different wobbling and tilting, that obliquity is the tilt. It all kind of lines up with these ice age cycles, and that people thought that couldn't be a coincidence. And ultimately, the science of this is super complex, but it all has to do with how the sun is hitting the Earth. And there are times where the sun is hitting the Earth in such a way that it's more favorable for a warmer planet, and there's times where the sun is hitting the Earth in such a way that it's more favorable for a more extreme and colder planet. So this super complex picture again emerges when we're talking about paleoclimatology. We have these Milankovitch cycles that are influencing kind of the way sun is hitting Earth. We also have biological processes that are producing greenhouse gases or taking them out of the atmosphere, such as photosynthesis that removes carbon dioxide from the atmosphere, or decomposition that creates carbon dioxide and methane and adds it to the atmosphere. And when we're talking about Earth's current climate stage, whether or not we're freezing with giant glaciers over Chicago, or if we're in a nice kind of warm state like we are today, it is a combination of these two things, and probably the Milankovitch cycles are also influencing these biological processes. And that is the kind of full picture of Earth. And you probably appreciate now that, holy cow, Earth's climate is unbelievably complicated. And that kind of brings us to present day global warming and climate change, and why everybody's making such a big deal out of it. The Milankovitch cycles and the biological processes that are currently happening on Earth are pretty much non-existent in importance compared to human activities. These natural processes are super slow and super small changes. And what humans are currently doing to the planet is anything but slow and simple. Let me give you an idea of what's happening. We just looked at some data showing the various ice age and warmer periods of Earth over time, and we saw that those related and lined up pretty much perfectly to the greenhouse gas carbon dioxide. When we analyze this ice data, pretty much the highest atmospheric content of greenhouse gases of carbon dioxide is 300 parts per million that we see. So if we look at all of the atmospheres of the last 800,000 years, the highest the carbon dioxide ever got in the atmosphere of the Earth is about 300. Currently, we are not at 350, which would be about here. We are not at 400, which would be what, around here. We just hit 420, which would be up here. That's how much carbon dioxide is currently in the atmosphere. Which means that if we actually want to make this graph accurately, all of this carbon dioxide was pretty much put into the atmosphere in the last 100 years or so. 100 years on this graph would be about the width of that line. I mean, that's the last 100 years. So if we want to actually make this accurate, what it would look like is this. And increasing each day. So we've pretty much taken the amount of carbon dioxide in the atmosphere and we've completely taken it off the chart to a place that was higher than the highest by an enormous magnitude. And what we can see is that there have been times where it looks like there has been a relatively quick change in the amount of carbon dioxide, where it's gone up from, 200 to, 280 in a matter of several thousand years, and that seems fast. We've done over 120 parts per million in about 100 years. So we're completely off the charts in terms of carbon dioxide. We appear to be slowly going off the charts in terms of temperature as well. This is the famous hockey stick curve. This was published in the early 2000s. So you can see the dates aren't current. We could extend this out to about 2020, would be about here. And since this was published in the early 2000s, actually our temperature, it has increased a bit more. We're at least at 0.8 to 0.9. And some even think we're higher, more like 1.2 already. So this is also kind of increasing off the chart as well. So this is just current temperature data. And we have a really good idea of this last 1,000 years or so of temperature data from all kinds of paleoclimatology indicators. The big question is, where are we heading with all this? So how hot is it actually going to get on Earth? By the way, before I move on, I think it's pretty clear from this data where we currently are. There is no natural process in the last million years has gotten us anywhere close. Actually, no natural process in the last 50 million years has got us anywhere close to where we are. And in terms of how fast we got there, there's no evidence in the history of the entire 4.6 billion years of Earth that we've seen this kind of increase in carbon dioxide this rapidly. The only explanation for how it's increased that much is human activities. And pretty much everything we do, and we're going to get into that next lecture, everything that we do on our planet Earth pretty much is putting carbon dioxide into the atmosphere. So how high is this actually going to go? I happen to have the data from one of the ice cores as part of a lab that I did a while back. So the actual data from the ice core, you can make what's called a regression of carbon dioxide and temperature. And basically what we see is a trend line that as in Earth's history, as you tend to increase carbon dioxide, so as we go from low to high, we basically see an increase in temperature as well. So we go from a lower temperature or a colder temperature to a higher, warmer temperature. And so we see this overall trend. Right now we are at 420, which is it would be like way off the screen onto my right side. So if we increase kept going on this trend all the way until we got to 420, what temperature would we be at? What do we expect for the Earth at this current level of carbon dioxide? And the answer is about plus 10 degrees is currently where we're at. And again, that number is rising. We've only made it 1 degree because there is a kind of lag effect going on. Luckily for us, there's a bit of a lag effect going on. If you imagine somebody coming out of frigid water or something and they're really cold and you put a blanket on them, it's not going to instantly heat them up back to where they were. It's going to take some time. And similarly, carbon dioxide in the atmosphere kind of acts like that blanket as well. So you do see this lag effect, but assuming that we maintain levels of 420 or above, we're going to eventually see a 10 degree increase, potentially something like that, a 10 degree increase across the entire Earth, Celsius, which is closer to 20 degrees Fahrenheit. So if you thought it was hot in Houston before, holy moly, it's going to be really, really hot. So, you know, we could really be going off the chart here. What would that actually look like in the world? Again, we can actually look back in our paleoclimate past about 55 million years ago, when scientists studied sediment layers from that era of time. They see that Earth, we believe, was between plus 5 degrees and 8 degrees Celsius above what it is now currently. So that was what we call the Paleocene Eocene thermal maximum. Paleocene Eocene was the era, like if you've ever heard of like Jurassic Park, that the Jurassic is like an era of time. Paleocene Eocene is eras of time, or is it aeons or periods? Whatever, it's like a time period. What we're pretty confident happened at that time period from other sediment samples and patterns of rock formation and stuff around the Earth is that pretty much every glacier on Earth melted. All of that water that was in those glaciers basically ran off into the ocean, and the oceans rose somewhere between 300 and 400 feet, or is it meters? It's a big number. And this is actually what we think planet Earth looked like. Everywhere you kind of see this whitish color would have been a shallow sea of flooded areas. Of course, the continents weren't quite in the positions they are today because it was 50 million years ago. But you can see, if this happens again, you can appreciate the scale of magnitude of what kind of changes are going to be happening to Earth. And it will all be man-made. To me, this is what kind of clarifies what's at stake. Houston is about 50, 60 feet above sea level where I'm at right now. You know, there would be hundreds of water over our heads if it got that hot on Earth. And all of Antarctica melted and all of Greenland melted. Luckily for those effects to happen, we're probably still centuries away. But, you know, I don't know if you've noticed some of the weather lately in the world, but it's pretty clear that some of the early effects of this global warming and climate change are already happening. Earth's entire climate system is just completely dependent on heat. As you add more and more heat, who knows what's going to happen, because it's inherently kind of a chaotic system anyway. And then when you add on top of it all of this paleoclimatology stuff, the history of Earth's climate, you realize, like, we're currently kind of, humanity as a whole is doing an experiment. We have no idea what the outcome is going to be. We are pumping in so much greenhouse gases into the atmosphere that we're taking us to places that we haven't been for millions of years, maybe ever, if we keep going. And the amount of warming that we can logically expect to happen based off of this paleoclimate data is absurd. The idea that somehow humanity is going to make it through this unscathed over the next few centuries is absurd. And even thinking, like, you hear these ads of companies saying, oh, by 2050, we're going to try to be carbon neutral, and that, governments are setting these kind of guidelines that by 2040 or by 2050, we won't be adding any more CO2 to the atmosphere. So we still have another 30 years of burning oil, coal, and gas and adding more carbon dioxide to the atmosphere. We're already at 420 parts per million. So what are we going to go to 500, 600 parts per million, where we could expect 20 degrees warming? And then the expectation that you see is that, oh yeah, if we stop CO2 by 2050, warming will be limited to 1.5 degrees Celsius. Where are you getting that number? All of our paleoclimatology data indicates that we are already cruising towards 10 degrees in the next several centuries. Who knows where we'll be at the end of this century? Who knows what the effects of that are going to be, because we have this. Have you looked at air and wind currents and ocean currents lately? They're a mess, naturally speaking. You're going to add all this heat and we're not going to see any major changes in any of this stuff. I think hopefully now you're beginning to understand why I said that this issue trumps every other environmental issue, every other economic issue that you can think of by many, 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 many orders of magnitude. So we'll just leave it there for now. And what's going to be coming up in this series is going to be basically what are the current causes of man-made climate change. Clearly, this is not natural. We looked at all the natural data. We are way beyond natural currently, and our path is, we have no idea where we're headed. So what's causing all this? What are these sources of pollution that is causing it? That might help us figure out solutions to climate change. And then ultimately, we want to know what's actually going to happen in the immediate future, in our lifetimes, and our children's lifetime. So that's what will be coming up next, and I'll try to explain it to you as simply and concisely as I can. I tend to get long-winded. I wasn't too interrupted by my dogs today since the early interruption, so that was cool. Anyway, I will talk to you guys later. See ya.